Hey, this is Steven from Legit Tech Tutorials, and I wanted to start a new series that I kind of use to break up kind of the monotony with my other series, which is the water jet, the DIY metal mill, and soon to be the CNC CO2 laser cutter. So that one I'm probably going to start here pretty soon. So those are the three main ones. Oh, and also a CNC lathe. So whenever I get bored or some sort of, or it hits a kind of a, what's the word, a kind of a dull point in the development of those, the idea is that I will do some videos on this. This is a little side project, and I wanted to kind of do this one just to kind of add some more excitement into doing these development series again. So whenever it gets to the point where it's like, oh man, I really don't want to do a video today, or I don't really have any new information, or I'm waiting for parts, or I'm still thinking about it, or whatever, and I'm out of kind of the other projects, like I said, those four main ones. CNC lathe, the DIY metal mill, CNC laser, and the water jet. So water jet, we still have one more video to do. I'll probably do that one tomorrow, and then I have to wait till the tubing comes in, which is like 4 to 6 weeks or something. Then the metal mill, it's waiting for me to get started. Before I get started, I'm going to double check everything. I'm going to go to my my teacher at school, my ex-teacher, I guess you could say, the metal shop teacher, and kind of go over his thoughts. Then the laser will probably start pretty soon. Probably this week we'll probably start it. I mean, I already started one video, kind of a teaser, but we'll continue going on that one. Then obviously the shredder is done. The shredder's over. The DIY metal shredder. I mean the metal shredder, the reclaimer, and then the CNC lathe. But that's going to kind of be a side thing compared to the other ones. So that's kind of what's going to happen here. So that is my current timeline. Number one project I'm working on is the water jet. That one is in development, and then also I'll probably be, while I'm waiting for parts for that, I'll probably also be every Wednesday or so machining some parts for the DIY metal mill. But when I'm not doing, or when I want to kind of spice things up and change it up, and I want to do kind of a DIY project that is not connected to this production stuff, is more on my hobbies, then I'll work on this one. So what is this project? So that being said, maybe one per week, maybe one every other week, something like that. So what is this project? This project is a DIY dyno. If you guys do not know, I am a big car guy. I have two classic cars. I have a 1979 Rabbit diesel, which is my daily driver. That's what I used to drive to and from work and commute to other places. That guy I really like that car. And then my main project, which I had, so the Rabbit I've had for since about 6 months, and my main project is I have a 65 Mustang, 1965 Mustang, which, if you guys don't know, is the first year of the Ford Mustang. So that is my main project, and that one I had since I was 16 years old in high school. That was my first car. So that car is I'm doing a whole bunch of different stuff, and actually I have a whole nother channel dedicated to it. But I wanted to kind of do this for car stuff. I wanted to learn more about the engine and tuning and stuff like that. So obviously I have very limited space, and I don't want to pay to take it to the dyno all the time. Let me see. So I wanted to have something small in the let's see what it says here. So here it's saying, so a dyno run is about $99 for 3 runs, and that's basically what you're going to get for 1 run. Then you could change something and then do another run, then you could change something and do another run, or if they don't let you do that, you have to do 3 runs and then kind of average, and then that's what your car is getting, and then do a modification and then go back. So yeah, so I wanted to do a little bit more stuff with cars, and most of my cars are lower horsepower. My Rabbit's got like 53 horsepower. I do want to do a turbo on it, a turbo kit, so it might be pushed. I want to try to see how much I could squeeze out of it, and really what I would like to do is have a way, as you guys know, I'm an ex-engineer student, and now I'm a mechanical engineer by trade. I like to be able to synthesize, give a number to the stuff that I'm doing. So let's say, hey, I spent $150 doing this modification, and I got X amount of horsepower, X amount of torque, or X amount of gas mileage, or X amount of suspension, handling, or braking power, or whatever. So I like to add a number to what I'm doing. So if I do another mod, it's like, hey, I only got, let's say, 10 horsepower for $150, while this one I got, 30 horsepower for $150. So that way I could go back to my my YouTube channel and say, hey, this is the better mod to do than this one, because this actually gives this amount of performance. So instead of blindly going about doing upgrades, I could now kind of justify what I'm doing and explain why it's needed to myself and also my viewers and stuff. So I wanted to do I was thinking about doing a small dyno. Whether I do it or not, I think it would be kind of cool to design it. And I think, as far as I know, it's going to be a little bit on the easier side. And we're going to talk a little bit about that. So what is a dyno? A dyno, if you guys do not know, is for generally either electric or gas vehicles, and it's for stuff like scooters, ATVs, dirt bikes, street bikes, go-karts, automobiles, semis, semi-trucks, trucks, cars, performance cars, race cars, F1 cars, all different kinds of vehicles that rotate, that basically have wheels. Anything that has wheels can be used on a dyno, right? And basically what a dyno does is you get into your vehicle and you go through the vehicle's power band, otherwise known as revving the engine. You go from whatever the car idles at, 500 RPM or whatever, all the way up to 5,000, and then it will measure how much power that is outputting. And you can do a lot of stuff from that. You can measure how much fuel you're putting into the vehicle, and then you could see, okay, what is my efficiency? I'm putting in this much power worth of heat, of fuel, whether it's jet fuel or whatever, whether it's jet fuel, ethanol, diesel, regular gasoline, whatever. I'm putting in this much fuel and I'm only getting out this much amount of power. I'm losing a lot here. Or you could do AFR, air fuel ratio. Hey, I'm putting in. This is one of the things that I'm looking at. Is number one, being able to justify mods to say, hey, I did this and now I got this much extra horsepower for this amount of money, right? Basically horsepower to dollar, right? Relationship. The other one is I want to learn a little bit more about tuning, which has to do with air fuel ratio. So it's abbreviated AFR. So basically most cars, except for ethanol, that use regular gas, I don't know what it is for jet fuel, I think it's the same, but it's about 14. There's something called the stoichiometric AFR. Stoichiometric AFR. I'm really bad at spelling, so So here, the stoichiometric AFR, air to fuel ratio, and basically the ideal air to fuel ratio for most vehicles is like 14 to 1, 15 to 1, stuff like that. So they're generally very very precise. And then ethanol is a little bit lower because when it actually combusts, it generates oxygen. So when it says air, it actually means oxygen. Oxygen is an oxidizer, and you need that with fuel. So let's say your AFR is low, so that means that you have more fuel to air, and that means that you basically run out of air to oxidize the fuel. The burn starts, and then it runs out of air and stops. So you're pumping in too much fuel, and you're running out of air. So some of your fuel is now leaving the exhaust pipe unburned. That means you're wasting money, and it's not great for the environment because now you're just releasing gas vapor that then, when it leaves the tailpipe, if it's hot enough, it's still burning, and once it hits oxygen, it's going to finish burning. So basically, you're releasing this flame that you're not containing inside the engine and getting all of the energy out of it. So that's not ideal. And then if you have too much air, it could lead to overheating issues and stuff. But if you have nice cool air going in there, it could be better off. But that means that if you have more air than fuel, that means that you could be adding. Let's say it's a performance application, you could be adding more fuel to meet with that gas and be able to burn use all of the air as oxidizer. So if you're short on fuel, you could add more and get everything out. Get all the power out of the possible air that you have inside the car. So that's one thing that I want to do with the dyno. The main two things with the dyno. And another third thing is braking power. And I'll talk a little bit about that. About slamming on the brakes and how fast can you actually slow down, that kind of jazz. So let's talk a little bit more about what type of dyno that I'm thinking. Ooh, this is nice. I didn't see this one before. Okay. So here is an idea. So there's multiple types of dynos. There's hydraulic dynos. I guess you could do a pneumatic. I was thinking about a pneumatic one. I haven't really seen a design like that. But they have hydraulic, which is basically what happens is, so most dynos, you have rollers, right? So you have rollers that attach to the back wheels. The back wheels sit on these rollers, and they spin the rollers. And then the rollers can be sometimes attached to different things. And those things absorb the power of the rollers, of the engine itself, and you could read, because of what happens to the things that you attach to those rollers, you could read how much power or torque. Horsepower is basically torque times RPM. So you could measure how much torque, and then by having a sensor that's on the engine, you can measure the RPM and be able to have a graph that shows you the horsepower curve, which is this. So there's a couple ways of doing it. There's some simple ways, and what I'm thinking is probably going to go with the simple way at first. So there are multiple types of dynos. Let's see if it says here. Okay, so but it looks like this is just let me see. Okay, so here's a Wikipedia page on dynamometers. So we just abbreviate it short dyno. So we'll say that it's basically a dyno. So there's multiple types of dynos. We'll just abbreviate dynos. Eddy current, which is basically you move a magnet and you move a magnet inside of a coiled surface, inside of a coil, and you create a magnetic field that basically, because the world tries to keep things from moving. So whenever something moves, it tries to resist that movement to keep everything still. This world and universe that we live in likes equilibrium, things to stay the same and not move. So just like when you're running, you have wind resistance, you have friction against the floor, all that kind of stuff that tries to prevent you from moving. So same deal here. If you're rotating something inside of a magnetic field, it does not like creating a magnetic field, so it tries to stop that from happening. So you use that to absorb the horsepower of the car, right? A car or the vehicle or whatever you're using. Magnetic powdered brake, so I guess like a brake system, another brake system, electric motor or generator. So you could basically attach an electric generator, basically electric motor to it. And same deal as kind of the eddy currents, you generate power with it. And so technically the power that you dump in should be the power that you see out. Obviously there's heat involved, heat losses. So you could also read it there. Fan brake, well, that's interesting. So basically generate wind. So attach a fan to this thing and then use the power that it requires to move air to absorb the engine. Hydraulic brake, which is basically pressurizing water. So if you pressurize water, how much pressure that you get out of the water, the change of the water temp, etc. Force lubricated oil shear friction brake. So maybe that's rubbing, I think, with oil in between. So there's a certain amount of friction there when you have oil in between two surfaces and you rub the two surfaces across each other. Water brake, so same deal, pump, right? Compound dyno, multiple. So what I'm thinking of doing is building what's called an inertia dyno. So inertia dyno is very, very simple. Basically, what you have is you have a wheel, and then you have a sensor that reads the RPM of the wheel. I think that's the sensor right there, it looks like. So basically what happens is when you rotate the wheel, just like I said, in our universe, things try to keep other things from moving. The world tries to keep things from moving. So when you spin something, it has something called a moment of inertia. And moment of inertia is the resistance of rotation. So basically what happens is when the vehicle accelerates, the drum that you have that this wheel is sitting on is trying to resist being rotated. And that requires some horsepower to overcome. Now it's a very simple system and it's more accurate than most because if you get exact measurements on it and you get really, really good bearings and everything, because obviously this thing is running on bearings, you get really, really good bearings and you have a very, very good sensor system and a very accurate sensor system that could read the RPM of this drum and everything is very well balanced and all that stuff, then you can get a very, very good measurement. But you are limited on the horsepower that you could sink to it, because you could, once you let go, for example, if you're spinning this wheel, once you get off the power, that wheel's got a lot of moment, it's got a lot of inertia on it, and so it might overspin. It's just going to now it's actually driving the motor. It's just like when you're driving downhill in a manual transmission and you get off the throttle, it slowly runs the speed down, right? So you could imagine that if you're spinning something up really, really, really fast and then you let go, it's just it might continue spinning faster if there's not a lot of friction in the bearings. So there is that. So you have to be very, very controlled with the vehicle that you're driving with, that you slow down adequately. So obviously very, very cheap as far as the components. I mean, you just have a drum, or you could have a flywheel like this, and then you have a sensor that's reading reading either like a Hall effect sensor, where it's reading magnets on here, or you have holes drilled where it's and you have a gate sensor where it shoots a beam from this side to this side and it just sees the beam. That's kind of how garage doors work. You have a emitter on one side and a detector on the other side. When you block the beam, it knows that something's there. So you have, for example, a whole bunch of holes cut in this, and then you shoot a beam from one side to another, and when there's no longer a hole there, it cuts it, and then it knows kind of where it is. And then you could have very, very precise holes drilled in this, and you could see that, hey, there's like 30 holes or whatever, and then you can know exactly where the wheel is over time, and then you can measure the exact acceleration, not the speed of the drum, but how fast the speed is changing. So acceleration is the change of speed of the drum. So let's talk a little bit about, we could look here, they have a little calculator, which is pretty cool. So performance trend engine inertia dyno sizer. Type in the requirement information, prediction, whatever. I've never seen this before, so this is kind of interesting. So max horsepower, let's say we have 110 horsepower. Max flywheel RPM, let's say we have 5,000. Measurement units, inch flywheel outside diameter. Okay, so this is interesting. So, but this is with a flywheel, and we're going to talk a little bit differently. So, let's go into moment of inertia and what that is. Hopefully, yes. Okay, so again, we're talking about an inertia dyno here. So you can see here a big, let's close this off here. So you can see here a big ring. Now there's actually different objects, right? So different base objects. I mean, you could calculate the moment of inertia for pretty much anything, but what we're looking at is polar moment of inertia, which means that it's not a 3D object, it's a 2D object that's extruded, right? That's basically symmetrical on the X and the Y plane, right? So these ones are not. Some of these are 3D objects. But if we look at this little animation here, let me go ahead and scroll in. Oops. So if we scroll in here, this is an exact idea of how you could picture moment of inertia. So if you see here, we have 4 different shapes. We have a spherical shell, which means that basically it's a sphere, but it's hollow on the inside. And then we have a solid sphere, a cylindrical ring, which means that it's a cylinder, but it's hollow on the inside. And then we have a solid cylinder. Now, you have an incline at the exact same angle, all the exact same friction, same distance to the end. Everything's identical to each other. Obviously, wind resistance is probably neglected, but that's fine. So, what you have is you have the exact same force from gravity acting on all 4 of these objects. Now, what happens is the moment of inertia is different from each object. And remember that the moment of inertia is the resistance to movement, to rotation, basically. So we see that here, the fastest is actually the solid sphere. And so what that means is that has the smallest moment of inertia. That means that needs the least amount of energy or force, least amount of force to get it to rotate. And it looks like the second lowest is the solid cylinder, which is this blue one. Now that requires the second least amount of moment force to get it to rotate, which means that it has the second smallest moment of inertia. Then the third is this shell sphere, which obviously is very difficult to manufacture, to have a solid sphere but the inside hollow. And then the last one is the cylindrical ring. Now this is key. So basically what that means, because the idea with this machine is that I want it to be not like a massive heavy thing that I have to lug around. I want it to be something that I could pick up off the shelf and put it on the ground, right? So I don't have to, a lot of these dynos, they have, you have to have a forklift that brings this thing over. So what that means is that I could minimize the weight. See, a lot of these, they do solid rollers, right? And you can see that with basically, and here it says identical masses. So everything is all the same weight. So identical masses and radii, so everything has the same radius, and also it has that same incline again, and same friction, everything. So for the same mass on the solid cylinder, and right, I showed you that on these guys generally use a cylinder. You could see that it has about double the moment of inertia, right, for identical mass. So what that means is that if you want the same moment of inertia between these two, you could actually decrease the mass quite a bit. So let's talk a little bit about the math involved here. Okay, so shapes, basic shapes. So let's look at some basic shapes here. Okay, cool. This is perfect. So here is a moment of inertia of standard uniform objects. So if we look here, solid disk. So this is like a flywheel, 1/2 mr squared. So m is mass, r is radius, right, squared. But we don't want it here, we want it about the center. So disk with hole, blah, blah, blah. Okay, so here's a solid cylinder, is 1/2 mr squared, right? Now let's say here it's a cylindrical shell, so let's see how they are different in weight. So 1/2 m a squared plus b squared, right? So I called my local steel store, and I found out that they have a 8-inch ID by 8 5/8 OD steel, A36 regular steel cylinder. So so with this, obviously I need a length to figure out the weight and then design it in CAD and then just have it tell me the weight. But with this, we could determine the difference between a solid cylinder and a ring. So here, let's see, we have two different equations here. So let me grab another little post-it note here. So we have 1/2 m a squared, which is the outside, and b squared is the inside. So 1/2, and it looks like it doesn't matter because it's adding. So 8 5/8, which is 5 is 6.6, 10, 25.625, right? 5, 10, 25, yeah. 8.625 plus 8, right, for that one. And then this one is solid, is 1/2 outside, m 8.625 basically. So let's cancel out m and say m is the same, even though it's not, obviously. But 0.5 times 8.625 plus 8 equals, so this is 8.3125. Now this other one is 0.5 times 8.625. That's 4.3125. So that's a little bit under half, as you can see here. So with the same weight, if we have a hollow shell, we could get about double. We need about double the weight of the cylinder. So we could actually cut the weight in half, and have the cylinder be the right moment of inertia. So I'm curious here. What if we do? Obviously, this is talking about 8.3125. Flywheel thickness is So here it's 5/8 divided by half. So 0.625 divided by 2 is equal to 0.3125. So 0.3125, let's just say it was similar. £4.805 pounds. Gear the dyno to keep flywheel RPM below 5,000. Important, this calculator is not completely checked. Acceleration time is from 0. Oh, max flywheel RPM. So basically what it's saying here is that to go, if you have 110 horsepower and you have a 5,000 RPM limit of that flywheel, and remember the flywheel is this guy, which is 1/2 mr squared. So let's see if we have a comparable. Let's see what we have here. So let's say we have 1/2 m, and we cancel the m out, and it's r squared, right? 8.3125 squared. So what that means is that we have 0.5 times m, which we're canceling out, times 8.3125 squared. 34. But obviously you're not going to have the same weight there, because that weight's going to be way thinner, right? But if we had the same weight, then that's a 34. But you can see here we definitely need to increase the size. So here, but the fly weight here is only 2 kilograms. The last thing let's do here is I'm here in my CAD, and let's go ahead and start a new folder, and let's call it the dyno. So then let's do here, very, very simple, circle 8 divided by 8, and 8. Okay, so now let's extrude this, and I'm gonna say it's gonna be about, didn't I see my tape measure somewhere? I'm thinking 24 inches or so, because you're talking 300 millimeters. So I think the biggest tire I'll probably run on these is 300 millimeters or so, which is like 13 inches or something. So maybe even like 20 inches. And then let's do body, make sure that this is A36 metal. ASTM. Wait. I think it's at the end. A36. A36. Okay. Properties. 740.6. Oop. That's up there. 0.6. What the heck? 740.0. 605 divided by 16. About 50 pounds. Okay. So with that, so what we could do is we could do some sort of backwards compatibility with this really quickly before I close this guy, because we are already a couple minutes over. So it is 40, what was it? It was 46 pounds, so 46.29, let's say. Okay, so now to get the moment of inertia to match those, so let's see, where's that other calculator? This one. Okay, so this one here. So 8.3125 times this other one times 40. 46.3, let's say. That's 384.87. Okay, so that's the number that we want to match. So, let's put this sticky note. Oop, I took 2 sticky notes off. So, let's do that 1/2 MR, and then we can basically have this calculator solve for us. So 1/2 M, well, then basically we're going to have to solve for M, pretty much. MR. Or we could just say the mass so mass obviously has nothing to do with the thickness. So here we could see that with this 8.3 it's 0.3125. So we kind of divide that by this 2 and then kind of come up with a scalar 2.179 divided by 0.3125. 2.179 divided by 0.3125 is equal to. So this is equals to 6.9728 pounds per inch thickness. Okay, so now we're back here, and what we're going to do is we have 1/2 MR squared. Let's keep the R squared the same. So this is 8 R equals 8.3125, and then basically we're going to solve for M pretty much. In order to equal 384.87. So 384.87 times 2, we're basically going to solve for M, over R squared is equal to M, which basically we're going to convert from M to this thickness here. So 300, let's do this as quickly as we can. So, oops, let me move this back. So 3, and here we're obviously going to get a rounding error because I'm going to do it simply, times 2 divided by 8.3125 squared equals. So that is 11.14 pounds. Wow. Okay, now take that to thickness. Then we need a thickness. Then the thickness here, we divide 6.9728. So this divided by 6.9728 equals. So it's 1.6 inch thick. So 1.6 inches thick. Let's see what it says. What did it say? It said 0.02, I think, last time. 0.3125. What did it say last time? Yeah, 0.02. Oops, 1.6. So that's not very fast. Acceleration time, you want to be at least here. So we could use this to solve. I'd say 10 seconds. It's 10 seconds. So how thick would this have to be? Like 5 inches? Wow, it's gonna have to be massive. Okay, so maybe 5 seconds. Okay, so maybe, well, we'll have to see what we could do. So I will look into it, and I'll watch some dyno videos and see how quickly they go up to speed. and we'll kind of go off of that. Alright guys, thank you for watching first video of the DIY dyno. Ooh, we're at 40 minutes. Thanks for watching, take it easy, and I'll see you in the next one. Peace.